Okay, so the third presentation in this session is given by Nicolas Navet. He's associate professor at the University of Luxembourg, and he's working in the field of communication and networking. Please, it's your turn.
Thank you, sir. So, I've been working for a number of years in the design of CAN-based architectures, especially on verification activities at early stages, early design stages, and I wanted to share with you my experience, and some views on that. And specifically today, I'd like to advocate for the use of simulation, but with a proper methodology. And we'll discuss simulation versus schedulability analysis, which is the other technique that is often used early stage when we do not have the real systems at hand. We have to work on models. Okay, so let's have an overview of the presentation. So first, we'll define what is simulation and what is schedulability analysis. Then I'll discuss what I think are the main shortcomings of schedulability analysis, and we'll see why it might not be necessarily the best techniques for every needs we might have. And then we will see how the use of simulation might be of help for the designers. Okay, and how to put a simulation in use. So first of all, let's define what we are talking about. So what is schedulability analysis? Well, schedulability analysis is a mathematical model of the system, and basically it comes to identify the worst case possible situations that can occur. For instance, in the simplest cases, it comes to the so-called critical instance where all frames are released simultaneously and then are released with the highest possible weight. Okay, so once the worst case possible situation is identified, then it's translated into some equations, and then it's solved whatever the techniques. Basically, there are two conditions to be able to have a schedulability analysis. First, a bounded amount of work must be submitted in any time period. And second, the resource here, the communication bus, must be scheduled in a deterministic manner, which is the case on CAN, fortunately. Okay, so what are the upside and the downside of schedulability analysis? Well, schedulability analysis provides upper bounds on the performance metrics, so it's safe. Well, we'll see, we'll discuss that later on. The analysis is usually published in some scientific papers, so it is assumed to be correct. Okay, that's also will be discussed. On the downside, it's usually pessimistic, sometimes overly pessimistic. Okay. Also, the analytical models may not be able to capture all the peculiarities of the system, and specifically here of the communication stack. We'll also discuss that on with more details. And also something which is true is that it's not very informative because it's only provide an upper bounds on what we are looking at, be it response time or length of waiting queues. Okay. Now let's get to simulation. So simulation is a program that reproduces the functioning of a system. Okay. So that's a simulator. Well, the advantages of simulation is that the models can be closer to the real system because it's easier to develop. It provides all information what one may want, distributions, whatever. Well, on the drawbacks is that the upper bounds are out of reach. One may simulate as long as one wants. We are not sure to encounter, to identify the worst case possible situation. And that's also going to be illustrated. And, well, as all computer programs, the validity of the model and of the simulator is unsure. We'll see what we can do to alleviate this issue. Okay, now, it's not that I want absolutely to include some advertisement at this point, but at least you need to know that I'm involved with the company Real Time at Work that I've created 7 years ago, which is a company specialized in simulation and timing analysis tools, and specifically timing analysis tools, analyzing tools for communication networks, including CAN and CAN-FD. Okay. Okay. This being said, now I move on to the rest of the presentation. So. My main message would be to not trust blindly models, be they simulation or analytic models. So what we hear often, is that schedulability analysis ensures safety. Okay, it's often advertised this way. One can read, okay, schedulability analysis covers corner cases and things like that. Okay, our point here is it might not be so simple. We'll see why. Well, first thing is that analytic models are pessimistic, except in the so-called ideal case. We'll see what it means in the case of CAN. Well, they might not be realistic as soon as there is we are not dealing with the ideal case. And finally, analytical models and their implementation can be flawed, just like any other program or analysis, but we'll see that it might be perhaps more acute in the context of schedulability analysis. And then second part of the talk will be devoted to simulation. So the 2 points that will be discussed is that it's possible to some extent to verify simulators and simulation model. We'll see how. And that with some proper methodology, simulation can provide guarantees and the user-chosen guarantees in addition. Okay, so those 5 points will be discussed and illustrated in the rest of that presentation. And for the illustration, we will consider, so you'll see results of experiments, and we'll consider a typical CAN-based automotive communication architectures with 2 CAN buses interconnected by a gateway, so 2 500 kilobits CAN buses, 20-something ECUs. And you see the load 50% on one network and 38 on the other network with something like 115 frames overall. We'll consider a random ECU clock drift. So you see, clock drifts are drifting away. So with typical values of several hundreds ppms. And we are using also optimized offset assignment so as to, which is among the practices of today, as discussed in the first talk. So we are using optimized offset assignments to schedule the frames. Okay, now let's see what. So the performance metric we'll be interested in is the response, the communication latency, also called the response time. So how is it defined? Well, it's defined as the time from the transmission request until the frame is received by consuming nodes. Okay, that's communication latency. So here, that's a view of a communication stack of an ECU. So the communication latency is made up of four main parts. Well, delays in software. For instance, if there is a communication task, the communication task might be triggered periodically, and then the frame might not be enqueued as soon as they are ready. There might be some latency here induced by the software. Then the frames are put the frames are put in a software queues, which might be FIFO or ideally prioritized or something in between. And then when there are empty transmission buffer at the communication controller level, then the frames are forwarded to the transmission buffer and they can participate to the arbitration. It takes some time because the frames might not be the highest priority at the time. And then, of course, when the arbitration is won, the transmission time. So that's the 4 parts. Well, what is ideal CAN? Ideal CAN is a system when, in short, every node is able to enter into arbitration the highest priority frame that is being waiting for transmission. It might not be always the case, and in the small picture here, you see there is a frame with an ID 1 which is in the middle, which is waiting in some queue. And so that ECU is not able to enter the highest priority into arbitration. It's because probably, well, it's a FIFO queue, not prioritized queue. Okay, so that's ideal CAN. And we will see that there are many reasons why communication stacks may depart from the ideal CAN. Okay, first illustrate the fact that analytic models are pessimistic. So you see a distribution of the response times, okay, that's the values and the probability in the y-axis. So, well, simulation max is the highest value that can be seen by simulation. That, in red, that's the worst case possible response time. Okay, we don't know necessarily, but that's the worst case possible response time. And that's the upper bound provided by schedulability analysis. So the bulk of the distribution can be seen on a test bed or by simulation. More infrequent events can be seen using long simulation, but there is a point where simulation is not suited anymore, well, at that point. And for the rest, we have to resort to schedulability analysis, okay? So there are 2 questions here, 2 interesting questions. What's the pessimism of schedulability analysis? Okay. What's the distance between the upper bound and the real worst case possible response time? Okay. And the second question, what's the distance between the simulation max and the actual worst case possible response time? Well, we'll try to at least give some hints on that. Well, that was an idealized distribution. A real distribution of response time, it looks like that. That's a medium priority frame on one of the bus of the architecture we saw. And so, of course, in many cases, in most cases, the response time is equal to the transmission time. Why is that? It's because it's a 50% loaded bus, so once every 2 transmissions, there's no frame to delay. Okay? And the simulation max is 3.7 milliseconds here, while the upper bound is 5.1. So you see there is a gap between the simulation and the schedulability analysis. But those response times are too rare to be seen, to be encountered during simulation. Even 15 days of here, it's 15 days of simulation, 15 functioning days. So you can simulate during the lifetime of a vehicle, let's say 5,000 or 7,000 hours, and you won't encounter such a response time. Okay, now let's move on. What's the pessimism of CAN schedulability analysis? In the ideal case, okay, without gateway, then the computed upper bound is also the worst case possible response time. We know that the situation can occur. Okay, so here on the graph, that's simulation max, and here that's the worst case response time. And we know that those cases can occur. We can resimulate them. So you see all those area correspond to cases that can occur, but which are too rare for simulation. But if it's unlikely to occur once in the lifetime of a system, is it really a problem? Well, that's up to the system designer to answer such kind of question, but at least it should be asked. As I told you, it's possible to resimulate the conditions, the situation leading to the worst case response time in the ideal case without gateway. And we can resimulate, and we see that actually they can happen, those worst case response time. Now, let's consider the case where there are gateways. Okay, we have several buses interconnected by gateways. So here you see that the simulation max and the same curve. Simply here, there are some frames that are forwarded from one network to another. And, and here we are interested, of course, in the end-to-end response times. So what we see is that the response times for the response time given by schedulability analysis are much higher for the frames that are forwarded. And we are not able to see that in simulation. And why is that? It's because the analysis is done with assumptions on each bus that cannot occur at the same time. So in that case, the schedulability analysis is pessimistic, and we know that it's like that. Okay. Third case, we are no more in the ideal case. We have communication stacks that are not with FIFO-queues. We'll see with a limited number of transmission buffers. We'll see reason why later on. So we are in the non-ideal case, and in that case, schedulability analyses are very pessimistic. How pessimistic is it? Well, pessimism is up to the longest possible busy period on the bus. So, for instance, if you consider a FIFO queue, a way to consider a FIFO queue is like any frame would have the lowest possible priority on the ECU. And thus, it will result in a response time which is the one of the lowest possible frame on the ECU. So the pessimism, well, can go up to the longest busy period on the bus, okay? Which is the worst case response time of the lowest priority in the idle case. Okay, just to illustrate that as soon as we are away from the idle case, then accuracy is much less. Okay, now the second point, and perhaps more important point, is that analytic models may not be realistic if the system has not been conceived with schedulability in mind. Okay, and why is that? Well, there are many reasons why a communication stack may depart from idle CAN. Well, you can have non-prioritized waiting queue. You can have frame queuing not done in the priority order, but for instance done in the order of the configuration files. Okay, you can have non-abortable transmission request here. Well, imagine you would have the one here. You would have to abort one of those transmissions to fill the buffer with the one. If you cannot abort the transmission, then it's a departure from the idle CAN. You may not have enough transmission buffers. You may have delays, and you have delays in refilling the buffers, actually. And, okay, you may have delays in producing between the time data is ready to be transmitted and the time the frame the transmission request is issued. So all those delays are not accounted for in most schedulability analyses. And anyway, there's no comprehensive global analysis that would be able to integrate all of them. Now, let's go further in the same line. As see now, we are looking at transmission patterns that might not be that might be different, that are different from the typical case of periodic frames with jitter. Well, one may have to model segmented messages, for instance, for code upload. One may have AUTOSAR-like mixed transmission models with a periodic transmission and sometimes between two periodic transmission and a aperiodic one. One may have diagnostic requests, okay? Well, we have transmission errors. So how transmission errors, how to include transmission errors into a deterministic schedulability analysis model? Well, there's no good solution. It's the same for aperiodic traffic. Gateway traffic also raises issues because the latencies on one network becomes jitter on the second network, so the transmission patterns are not the same anymore, and so on and so forth. So all those reasons are all those transmission patterns may not be perfectly captured by analytic models. Okay? Well, now, if the analytic model does not capture all the characteristics of the system, then the result will be wrong, okay? Which means in some cases unsafe. But what's difficult is that they are wrong in an unpredictable manner. So for instance, that's two curves. Out of 15 ECUs, there is one ECU with a FIFO-Q. And the results in red with the FIFO-Q out of 15 ECUs, well, are very unpredictable. And in that case, well, to the best of our knowledge, there's no schedulability analysis published yet for both frame offsets and FIFO-Qs. So how to do that? Well, either you overlook the fact that you have FIFO-Qs and your model is wrong, or you are not using frame offsets, and then you are very pessimistic. So there's no good solution in that case. Now, I'll conclude about the suitability of schedulability analysis for non-ideal architecture. The good news is that there are a couple of research groups working in that direction to bridge the gap between analytic models and real systems, and I gave a number of references. Well, there are a number of bad news. Not everything is covered, no integrated framework, okay? Many existing analyses are very conservative, which makes them not very much usable for highly loaded systems. For 70 or 80% systems, it does not work. Well, another problem is that a comprehensive and exact analysis would be overly complex. We've tried that before, and it's too error-prone. So I think the best solution is to resort to more coarse-grained analysis, but at least that we know correct. And more analysis might become intractable in the computer science sense, which means that there's no polynomial time solution. And it's the case as soon as you are using offsets. So my view is that both accurate and comprehensive analyses are out of reach, okay? But if you need analysis, then you need to conceive your system accordingly. You need, for instance, to have a very specific requirements with regard to the suppliers. And yes, schedulability analysis can be flawed. There are sometimes. There is a famous example. Well, the first 5 minutes. Okay, I'll speed up. The first analysis was published at the ICC in '94, and it took 13 years for someone to figure out that the model was wrong. It's being used for 13 years. It was slightly wrong, but okay. So, and it was a very basic analysis. Now it's much more elaborate. Okay, implementation are error-prone because of the complexity, because of floating point arithmetic. As soon as you are using floating point arithmetic, you are in danger. It's not easy to check correctness. Okay, there are not many end users, and so on and so forth. So there are solutions. Okay, I won't discuss that. Perhaps the more important is that the analyses are published, okay, and that the software documents very well what is within the box and what are the assumptions to use the analysis. Okay? Now, it's the same for simulation model. Why? One can question the validity. Okay? Well, it's possible to validate to some extent simulation model. It's possible by resimulating worst-case situation from the schedulability analysis. Okay? It's possible by by comparing with real communication traces. Of course, in real communication traces, you don't have response time, but you have inter-arrival time. So you can compare inter-arrival times. And you can check properties on communication traces. I don't go much. Of course, for the simulation model to be correct, to lead to correct outcomes, then you need that the model parameters are realistic. So it means that the transmission patterns are okay, transmission errors are correctly modeled, clock lifts are taken into account, communication stacks are modeled correctly, and so on and so forth. And here's analysis of communication traces is helpful. Now, in a few, let's discuss the final part of this presentation, which is about the use of simulation. So, our proposal is to use quantiles. It's a widely used measure of risk. For instance, in finance, it's called value at risk. So, what is quantile? Well, a quantile, Qn here, is the smallest value such that the probability to have larger response times at this value is less than 10 to the power of minus n. Let's have an example here. Between Q5 and the simulation maximum, the probability mass, the number of events occurring in that, the probability that, well, it means that one frame every 10,000 is in that interval. Okay, so you can control the risk. So how to use it? Well, first you determine the criticality of the frames. Then from the criticality, you know what is admissible in terms of deadline miss. Okay, if you can afford that one frame every 10,000 does not meet its deadline, then you just have to make sure that the latency constraint is larger than the Q5 quantiles. Okay, that's the idea. What is nice with quantile is that it converges, it's reproducible. You can control the confidence interval. Well, there's no in other fields such as finance, they are trying to figure out what would happen in outside the traces, but it's not the case here. We are just looking at communication because we have enough data in our case. Okay, now first question: how often a performance objective can be violated? For instance, Q6. It means that one frame every 1 million will, in average, will miss its deadline. So if we consider a 10 millisecond frames, it translates into one deadline miss every 2 hours 45. Is it acceptable? Well, it's up to the system. For 500 millisecond frames, it's 5 days and 19 hours. Okay? There is a warning here, is that successive failure can be temporally correlated, and this should be ruled out. So you can do some, if you have, you can do some analysis to check for linear or non-linear dependencies in the traces. Okay, but this being said. And now, once you have determined the quantile, okay, the good quantile for your application, then you need to know how long you need to simulate. Well, it's not an obvious question because you don't have, you could use confidence interval, but we don't have a theory for that because we are in cases not covered by the theory. So, well, I don't go in detail, I don't have time anymore, but basically the answer is you need to simulate sufficiently long so that the simulation converges, which means that if you reproduce the simulation, you would get about the same result, okay? So typically it's a few tenths of occurrences. Okay, but you cannot do that by hand each time. You can have tool support for that. For instance, in our simulator, you see the figures in gray indicate that those numbers should not be trusted. Okay, and the one in light gray should not be trusted at all. It means that the simulation length is not enough. Now, just to give you an idea, for typical systems, Q5 or Q6 are okay. You can obtain that with a few hours of simulation, okay? With the example, the automotive example, 2 hours of simulation were enough to obtain Q6. Okay, I'll skip this slide and move on to the concluding remarks. So, first thing that I wanted to stress is that there is a gap between analytic models and non-ideal real systems, okay? They are pessimistic at best and unsafe if the assumptions underlying the analysis are not made. Well, at least, I do not foresee a big improvement in the years to come in that line of work, I would say. And if analyzability is a design constraint, then if analyzability is needed, then it should be a design constraint, and it has a number of implications and regarding the system design. Okay, you cannot reuse. You have to be very strict regarding the suppliers. You have to specify many things. Now, simulation is a practical alternative even for critical systems, provided it's being used with some proper methodology. So the idea is to determine, what we suggest is to use quantile, to determine the quantile with regard to the criticality of the set of messages or the frames, and the simulation length with regard to quantiles. And of course, you should use models and simulators that have been validated. You should not trust simulation models as well, no more than analytic models. Oh, something. So if you have been interested in that, there's going to be a paper with Mrs. Louva from Renault and Mr. Villanueva and Campoy Martinez from Renault, as well as Mr. Miege from Real Time at Work. That paper is going to discuss more how it's being put in use, and it's going to appear at RTSS. And of course, you're welcome to the RTOW stand if you'd like a demo. That was it for me.